Okay, y'all, it's time for an extremely famous example of a mathematical theorem using proof by contradiction, and that's the fact that the square root of 2 is an irrational number. Okay, what does this mean? Recall that the set Q of rational numbers, I'm going to write this in set generator notation, it's the set of all numbers of the form a divided by b, where a and b are integers and b is not equal to 0. So this is the set of all numbers that can be written as fractions of integers. This is called the set of rational numbers. Set of rational numbers. Okay, so big famous theorem. This theorem goes all the way back to the ancient Greeks. So theorem, the square root of 2 is not in the set of rational numbers. Another way to write this is that square root of 2 is irrational, so a number is irrational if it's not rational. And another way to write this is that there does not exist a or b in the set of integers such that the square root of 2 is equal to a over b. So that's kind of the formal logic expression of this idea, and that's the one that we're really going to use in our proof. So how do we prove this? How do we show that there's no possible choices of a and b that would give you the square root of 2 when you divide one by the other? This is a pretty common scenario for proof by contradiction. If I say that there's no possibilities, a pretty common approach here is to say, hey, well, what if there were some possibilities? And show that somehow that puts us in an impossible spot. So let's go ahead and do that proof. Okay, so I'm going to start by supposing the opposite of what I want to prove. I want to prove that 2 is not, or the square root of 2 is not in the set of rational numbers. So I'm going to suppose that the square root of 2 were in the set of rational numbers. This is what I'm going to show leads me to an impossible situation. So if this were true, then it would be the case that there do exist a and b in the set Z with the property that square root of 2 is equal to a over b. So what I'm going to do is I am going to consider such an a and a b. Furthermore, I am allowed to assume, I can assume that a over b, this fraction, is in lowest terms. Lowest terms. And what I mean by lowest terms is that there is no common factor that I'll call k of either a or b. So this means no k that divides a and b. Now, why am I allowed to assume this? This doesn't seem like something that was in the statement of my theorem. Why is this an okay assumption? The reason is that if I had such a common factor, well, if I had such a common factor, I could have picked a over k and b over k instead. If I had such a common factor, I could have just divided both my a and my b by that common factor. That wouldn't change the fraction, and then I would be in lowest terms. So this is a free assumption. Sometimes we call this an assumption without loss of generality. I can assume that we're in lowest terms because if we're not, I can make an easy modification to make sure that we are. Okay, so now it's time for some algebra. If a over b is equal to the square root of 2, then it must be the case that if I square both, I'll get a squared over b squared equals 2. Or if I just rearrange this, a squared equals 2b squared. Therefore, by definition, a squared is an even number. A squared is even because I've written it in the form 2 times an integer. B squared is an integer because b is. Therefore, a squared is even. We previously proved that for any n squared is even if and only if n is even. So if I use that result here, I know that a squared is even, and therefore a is even as well. Use that result here, previously known result. I know that a is even as well. So a equals 2 times j for some choice of j in the set of integers. Okay, but now what I'm going to do, let's check this out. But now I'm going to do some more calculating. Let's look at b squared. B squared is equal to a squared over 2. I got that just by taking this step and dividing by 2 on both sides. If I plug in what I just learned for a, well, a is equal to 2j, which means that this is 2j quantity squared over 2, which is equal to 4j squared over 2, which is equal to 2j squared. So if I look at this, I say, oh, b squared is equal to 2 times j squared. J is an integer. J squared is an integer. 2 times j squared is an integer. So b squared is also even. And therefore, using the same previously proven fact that we cited for a, b is even. However, and this is now where my contradiction comes from, but we assumed safely or without loss of generality we assumed that a and b had no common factors. So they can't both be Even if they were even, 2 would be a common factor. This is a contradiction. And our supposition that 2 is in the set of rational numbers must have been false. And that completes our proof. We started with a bad supposition and we derived a contradiction, therefore the negation of the supposition must be true. And the negation of the supposition that square root of 2 is an element of the rational numbers is what we wanted to prove. It's not an element of the rational numbers. The square root of 2 is irrational. One thing to notice about this proof is that we started with the supposition the square root of 2 is irrational, and what we ended up deriving as our contradiction feels a little bit far away from that. We ended up showing that 2 numbers that had no common factors actually did have a common factor. The common factor was 2. So this is a good point about proof by contradiction. The contradiction you get isn't necessarily always one that feels very deeply related to the theorem you're trying to prove. But that's okay. Any contradiction is enough. Any contradiction is enough to prove the negation of your supposition and therefore to prove the theorem.